Okay, let's start with the concept of oxidation reduction. And it's also called redox, a simple way of saying oxidation reduction reaction. And it's the transfer, is any chemical reaction which involves the transfer of electron. When you get a chemical reaction, A plus B gives me C plus D, mass is not created or destroyed. And the mass on the left side of the equation should be equal to the total mass on the right side. So that means that if a substance as A is losing electrons, another substance must be receiving because the electrons are not going to be lost. You have to have the same number of total electrons on the right side. So if this is losing electron, the electrons are being transferred to B. And that's basically the principle, the main concept on redox reaction. Now, redox reaction, to be able to recognize them, because you're going to be asked, for example, things like, well, is this a redox reaction? And questions like, which substance is being oxidized, which one would be reduced? And questions like, which is the oxidation agent, which is the reducing agent. But before we get into this video, this 15 minutes video, around 15 minutes, gonna be just in the definition of oxidation numbers and how to determine oxidation number of a substance. Why? Because to be able to recognize a redox reaction, we need to determine the oxidation number of the reactants, of all the substance involved, and of the products on the chemical equation or reaction. So that means that we have to go ahead and determine the oxidation number of all the substance involved and see what was a change during the chemical reaction. If there was a change, then it involves it is an oxidation reduction. So let's get into oxidation number. First of all, the definition of oxidation number is an assumption that all atoms in a compound, in a molecule, have a charge. And why did I say assumption? And this is very important to understand. And it's that when you have an ionic compound, I don't know if you remember this, in an ionic compound, you have a metal and a non-metal. Okay, in which the metal gives an electron or two electrons, depending on the charge of the metal and the valence of the metal, it gives the electron to the non-metal. So here you got a positive charge, okay, and a negative charge. Least electronegative element to the left, but the most electronegative element to the right, which is going to be accepting the electrons. Now, in this case, yes, the ionic compound, each element has a charge. Now, what happens if you have a non-metal with a non-metal? Well, it's a molecular compound, what is called, and they form a covalent bond. What does it mean if you have more than two nonmetals? Will form different bonds, but what does it mean? They share electron. So the real nonmetal here won't have a charge. It will be sharing electron, and this one either. But covalent bond, of course, there's going to be a difference between them, and usually the one on the left is going to be less attractive to electron than the right. Sometimes you have a molecular compound in which both of them have the same attraction, and this is called electronegativity. Electronegativity is the tendency, electronegativity, and it's the tendency, right, of of an atom to attract electron when bonding to another one through a covalent bond when sharing electron. That means that even between these two, they're sharing a pair of electrons. This is two electrons here, right? That if this element is more electronegativity than the one on the left, the electrons share would have the tendency to be on the right side. So, as I was saying, they don't have a charge, but the least electronegative element being on left and most being on right, we're going to assume that they do have a charge. So the least electronegative element, the one on the left, usually would have a charge of plus, which we will assume, again, a charge of a plus. It depends on which one. Like, for example, with the metals and non-metals, some of them would have a charge of +1, +2. Transition metal varies, and oxidation number varies. But some of them, for example, when you have a metal, an ionic compound would be identical as the charge. But let's go into something. I'm gonna have posted this handout, and if you want to purchase it, very little, and it's gonna be for very low cost. You can purchase this guideline, which is very helpful, because that way we follow the rules of the oxidation number, and it's gonna help us tremendously to determine the oxidation number of an atom, of an element. And basically, we have here the oxidation numbers of an atom of a free uncombined element is 0. First of all, when you look at the rules of oxidation numbers, the first rule given in these guidelines is gonna be um, that the first rule you're gonna apply. If it doesn't apply to the element, then you have to go for the second rule. If it doesn't apply, then you go and see the third rule. But the first one says, number one, uncombined element has a charge, oxidation number of 0, always. So if we have like O2, is 0. If we have um, hydrogen gas, is 0. If we have a metal like sodium solid, it's 0. Okay? And when we see in a little bit, we're going to see an oxidation reduction. But for example, if you have a combustion reaction, which is an oxidation reduction, a redox, plus oxygen gives me CO2 plus water, right? If you got here, right, let me balance it. It's balanced already. 2, 3, no, 2 and 2, 4, 4, oxygen, 2, and here would be 2 and 2, 4. So when you have here the oxygen, this carbon would have an oxidation number, this hydrogen will have another oxidation number, and this oxygen is uncombined. So if it's uncombined, we apply the first rule. The oxidation number is 0. Let's go to the second one. The second one is basically telling you that you have periodic trends that are going to be very useful to determine the oxidation number. And why are they useful? Because some of them don't follow those trends. For example, some of them vary the oxidation number. Let's say like the charges on transition metals. They vary. They could have multiple charges, the transition metals. So using these periodic trends, right? This third rule would be for oxidation number. And I'm go back for a second because it says 3, rule number 3, but basically this rule number 2. What I was explaining before is that the least electronegative element is on the left side of the compound. Generally, there are exceptions. And the most electropositive, least electronegative, and the most electronegative, the more electronegative element has a negative oxidation number. Okay, how I said. It's basically something very similar to ionic compounds. Because that's what we're assuming. Useful, but let's go now with the useful rule number 3. Hydrogen oxidation number +1 with most non-metals, -1 with metal. And as I give you an example, if you have NaH, here is a metal and a non-metal, and it's going to be +1, hydrogen -1. But what happened in water, for example? In water, right, as you see, oxygen is more electronegative, this would be always +1. But let's get that I mentioned water. Let's get into the rule, into the another trend very important. Oxygen is usually -2, except peroxides. And I'm looking at this in oxygen, if it's usually -2, of course, as I said, the first rules is uncombined 0. But if the element is combined, then we look for the second, third, fourth rule. And in this one, they give you useful periodic trends to determine. So here in water, oxygen always, always, always -2. And I say several times because it's a very useful tool that you can have when you're determining the oxidation numbers. So in peroxide, for example, hydrogen is always a +1 or -1. That's it, period. But here in peroxide, you have +1 for the hydrogen, and in this case, oxygen would be -1 because this is one of the exceptions. Now I'm going to explain several things about oxidation number. And I'm going to keep on going with the fourth rule. Now let me, and I'm sorry for this, but this would be rule number 3. And I skip rule number 2. Not really skip. If you remember, I just put it here. This would be the rule number 2, right? Here. The more electronegative element on the left, positive, the more electronegative element on the right, and it would be negative, and the least electronegative element or the less electronegative element on the left would be positive, and it's usually on the left. On the left. So this is rule. So let's get to more trends. And another one is helps also is one that the group 1A, right? They call the group 1A, 2A, and aluminum +3. They call it sometimes when you're naming compound type 1 and type 1. But basically it's metals which gonna have one single charge. It doesn't mean that it's +1. It means that the group 1A always gonna have +1. The group 2A always gonna have +2. And then, for example, aluminum is going to have +3 always. So that's another. And the following would be that the fluorine, right? The fluorine is always -1. And this is a very useful trend. And it's that the fluorine, right? Another one would be 1A. Hold on, a charge of +1, group 2A, a charge of +2. Fluorine would be fluorine would be -1 always. And then finally, halogens are gonna be combined with metals, and I'm gonna be -1, the rest of them. Then we'll see when they're combined with no metal because the charge varies. So chlorine, bromine, at least when they're always -1. When they're combined with metals, they always have that. And let's stop here, okay? And I will be recording a second part of this video on oxidation number.